Hi everyone, welcome to the 126th Stanford MedAI Group Exchange Sessions. This week we have Shantanu Ghosh from Boston University talking about his research on developing more efficient transfer learning and domain adaptation. So Shantanu is a PhD candidate in electrical engineering at Boston University, advised by Professor Kehan Bhatmangalich. He previously completed his master's degree in computer science from the University of Florida. His research interests lie in representation learning across computer vision, medical imaging, focusing on interpretability and explainable AI. And he specifically investigates the representation across different modalities, architectures, training strategies for generalizability, robustness, and trust. And as Shantanu mentioned, he you have a preference for people interrupting whenever they have questions, right? Okay, so
Sure.
let's make this session as interactive as possible. And without further ado, let me hand it over to Shantanu.
Yeah. Hi, everyone. Thank you for inviting me in this talk. So before giving this talk, let me give you a brief background about myself and how I come to this, interesting area of explainability, interpretability. So I completed my undergrad from what is called a community college in India back in 2012. And after that, it has been almost like 6.5 years. I have been a software engineer across two different companies in India. And then I, kind of got bored and I came to the US to do my master's and ultimately got interested into PhD. So one thing about software engineering was that I, even though I got bored, but there was one good thing about software engineering, which was that if you find there is a problem in the code in a software, in a software, you can quickly identify that where that bug is. You can go there, you can fix it very quickly, which will gonna make your output correct. Unfortunately, when I used to take when I was taking my deep learning classes, I saw this problem like the deep learning frameworks, they are black boxes, you cannot trust them. There is a whole lot of issues with explanation. The explanation often they are not consistent. So there are like a whole lot of questions, especially these questions were very apparent, back in 2019 when there is no way you can interact with a model. Now, of course, with Lava and ChatGPT, we can interact them with the model, but back then it was not possible. So that's why, I got interested into explanation, explainability, and I got into this research under the supervision of Kehan. And this talk, I'm gonna talk about a model explanation method, which will gonna help us to incrementally carve out a mixture of interpretable models out of a trained black box. So you all know that there is always a dichotomy between the interpretable by design models versus the post-hoc explanation. So this talk actually aims to bridge that particular gap. So yeah, let's begin. But first of all, why do we need the model explanation? Now, there are, of course, several reasons for that. The first one is trust. When we want to relinquish the control and the objective of the training and the deployment sites differ, understanding the model behavior is actually necessary. Another important reason is causality. Now, all these AI models, they are just encoding the correlation. What if we can use the model explanation to generate testable hypotheses, which can be formally tested with some extra experiment? For example, in this paper, the authors, they show causal techniques to gain mechanistic insights into genetic processes. Another important reason is transferability. Now, the question is, can these models help us to build more transferable AI models? Because the clinical knowledge or the rules, they are quite transferable from one hospital to another. For example, say enlarged heart size plays a key role to identify cardiomegaly, regardless the hospital or regardless the site. Now, our ML models, unfortunately, they are not so much transferable. We usually have to force them to learn these transferable patterns by learning across multiple domains. can we use the model explanation to make these models more transferable? And the fourth reason is informativeness. If the AI will be a part of our decision making, then only yes, no answer is not good enough. We actually need more insights of the decision making, like the clinicians. Finally, if we care about deployment, we need to make sure that the decision making of these models have to be fair and ethical. This goes way beyond than the classical performance metrics like accuracy, AURC, AUPRC. What I have to say is that the ethical implementation of AI goes way beyond than the algorithmic fairness. But yeah, that's a different topic of discussion, and I'm not gonna cover that topic. Okay, so what are the design choices that we have for model explanation? The first one is we can create a black box and explain the model post-hoc, or we can create or design an inherently interpretable model. Now, examples of post-hoc explanations are typical like saliency maps, feature attributions. There are like many methods that are already there, CAM, grad CAM, smooth grad, all of these, are popular example of these feature attribution methods, which actually highlight the important pixels that play a key role for the model's decision. There is a plethora of interpretable by design models are already there. For example, something like decision tree, proto-pnet, linear classifiers, all of them falls into the category of interpretable by design models. In this talk, I'm gonna specifically concentrate on a particular class of interpretable by design models, which are called concept bottleneck models. Now, in concept bottleneck models, you're gonna have these two components. One is the feature extractor phi, followed by a linear classifier. And the aim of these models is to predict the class labels. And along with that, it will gonna also predict the important concepts which play a key role for the model's decision. For example, here, the model is gonna predict the image as horse, and also it will gonna identify long neck, forager, and buck teeth as the most important indicating concepts for this particular class, for this particular sample. Okay, so there are pros and cons to each approach. In post-hoc explanation, we have got all the flexibilities of a black box, so the performance of the black box will not gonna be compromised. However, it leaves too much onto the human interpretation. And we all know that the human interpretation is subjective and it is vulnerable to confirmation bias. Also, previous research showed that the post-hoc explanation can often be inconsistent. For example, you can have same explanation or same saliency maps for two different classes. And most importantly, no algorithmic recourse is possible. So if we don't like something from the black box, there is just no way to go there and fix the black box. Okay, now for transparent models or interpretable by design models, they allow intervention. For example, in typical rule-based approach, if we don't like a specific rule, we can manually change it. However, the design choices are often limited. And more importantly, the interpretable by design models, they often achieve subpar performance compared to their black box variant. For example, when we deploy the concept bottleneck model to identify these diseases for mimic CXR dataset, we saw that they often attain subpar performance compared to the DenseNet one-to-one based black box models. So what will be the desirable properties that actually we want from a model explanation? We like the good performance of the black box and its flexibility. So the performance of the model should not be compromised in any explanation technique. We like the recourse property of the interpretable by design models, because if we don't like a particular property of a model, we can fix that bad behavior. And importantly, we want to focus on the transferability. After all, the clinical rules between different domains, they are invariant. For example, between different hospitals, the clinical rules to detect a particular disease, they don't change from site to site or from hospital to hospital. What are the examples of such rules? So here is one example. One of the rules says that if the A1C test is greater than 6.5% for both the visits, the patient has diabetes. And likewise, we can compress all these rules in the form of first order logic, which is shown here, P implies Q. So the idea is that we want to learn these rules in this P implies Q form in a way that the left-hand side, that is all the P's, they will gonna consist of the human interpretable concepts, and the right-hand side will be the class label, or in medicine or medical imaging, it will be the disease labels. And we're gonna extract those concepts from a trained black box. Okay. So the general idea is that these rules are encoded in the representation of the black box, and we want to extract them. So we start with a pre-trained black box model and incrementally carve our interpretable models in the form of first order logic that I just showed you earlier. We continue this process so that the contribution of the performance of the black box reduces at every step. And at the end, we will gonna have a set of transparent models that's sometimes in this talk, I refer to them as symbolic models because it uses human understandable concepts or symbols to, and we combine them in a symbolic function, which is the first order logic. So let me explain you first the setup. We assume that on the training data, we have the images and a set of concepts and the label. For example, here in this cartoonish example, we have the images as X's and the label, which is dog, as Y. And then we also have the annotation of the human understandable concepts or attributes as ears or like feet or brown texture of skin. And we also assume that we are given with a pre-trained black box, and the black box was trained to predict the label from the images. We also assume that the black box is actually decomposed into two halves. One is phi, another one is h. Phi is the feature extractor, h is the linear head. By feature extractor, you can think of this phi as all the convolution layers in a CNN or all the encoder layers in a vision transformers. Similarly, in a clinical setup, we assume that on a training data, we have the access to the images along with the radiology report. We extract the concepts by parsing the radiology report via an NLP pipeline. In this work, we use the famous rad graph to do so. The extracted concepts are the anatomical landmarks and the observed pathologies.
So actually, Shantanu, I have one quick
Yes.
question here because,
Yeah, sure.
For example, this is a perfect example that you are showing, right? While this may be infectious, so it is not a confirmation of the infectious. It is still a kind of maybe. So do you still consider
Yes.
those concept as your concept, extracted concept, or when there is like negation or worrisome, you are not considering that as your extracted concept?
So so this is actually just a template example. So if you look at the rad graph structure, so they have this hierarchy that your anatomies will gonna have some sort of impact for a different observation or a pathology. So we actually use the nodes which are coming from the rad graph. That's it. We are not
Because
like,
RadGraph is not taking into, that's my question, right? Like I know RadGraph pretty well. And
yeah,
RadGraph is not taking into account the negation and the worrisome.
right.
So are you
So we
taking
are,
it? Yeah.
no, we are also not
Okay.
taking it. We are also
Okay.
not taking it.
Got it.
Yeah. Thank you.
Because that is the primary difference between the normal captioning versus radiology report. Because in
Yes,
normal
yes,
captioning, when you mention an entity, the entity is present, right? But the
yes,
radiology report is kind of opposite. When they mention even like an entity, it can be negated.
yes. So when we actually created the rules So if something is negative, so it will have a negative value in the final weights, and we consider that as negative. So, but while creating the concepts, we actually did not use this negation from
Okay.
rad graph. Yeah.
Got it.
Yeah. Okay. So then finally, after extracting the concepts from the report, what we have is this triplet, which is the image, the concepts, and the final label. Okay. So remember that we start with a black
Sorry,
box.
can I have another quick question since you mentioned
No,
that?
sure. Yeah, sure.
Yeah,
Yeah,
because
sure.
for example, consolidation is also, you can consider it as a label, but you can also consider it as a concept, right?
Yes.
So
Okay.
do you use a
Yes.
duplication or no?
No, this is a very good question. So suppose for example, for Mimic, so we did our experiments for Mimic CXR and for Stanford CXR. So in Mimic CXR and in Stanford CXR, we have those 14 disease labels, right? So when we extracted all the concepts, we actually, removed those 14 disease labels from
Okay,
the
got it.
concepts.
So just to make
Otherwise,
sure that those concepts are unique, not same as the
yes,
label. Okay.
yes. Okay. So and also, like, if I want to give you a hint or a caveat, is that I think we extracted something like around 65 concepts for Mimic, and we actually use that in our subsequent method. So that's like a heads up.
Got it.
Okay. Yeah. Okay. So remember that we actually start with a black box model. Now, the idea is that the black box encodes the human understandable concepts in its intermediate layers. So the first step is to discover those concepts from the representation of the black box. How do we do it? We take the representation of the feature extractor phi and learn a linear projector T. This projector projects the representation of the black box to the concept space. More specifically, we train the projector to predict the concepts. Now, this is a very common step utilized in methods like concept activation vector or TCAV. This linear projector T will basically predict the probabilities of the concept being present. Here, they're actually represented using this toggle bar. And these concept probabilities will be the input to the downstream interpretable models, like the traditional concept bottleneck model. So is this like this, pre-step is clear? Okay.
I have
So
a question actually.
yeah,
So
go ahead.
when you're learning the concept using the projector here, it's always in a
Yes.
supervised setup. So you assume that you have labels for these concepts, or can be
Yes,
situations where
this is a good question actually. So for this work, we actually assume that our concept set is complete. But now I know that there are work going on which assumes that the set of concepts that you have, they're not complete. So you can use, of course, LLMs and large language models, to get those additional concepts. So this is a new area of work that is going on. But when we did this work, there was no LLM and things like that. So we assume that whatever concepts that we have, that they are like complete.
But I guess that's actually two aspects. You have a concept dictionary which encompasses all concepts that are possible in
Yes,
the dataset, which I think is what
yes,
you're referring to.
yes,
Also asking if for a particular, like each instance, do you have a label of these concepts are present or not? Like for example, in this
yes,
dog cat picture,
yes.
assume annotation.
We have that annotation from actually RadGraph. You
Got
can get all the annotation for each samples from RadGraph. So, that you can use that for the downstream prediction. So this T is actually trained or learned using that supervised fashion.
Got it. Okay.
Okay.
Thanks.
Okay. So once we know the concepts, what do we do then? We try to find a rule in terms of first order logic to combine these concepts or symbols and mimic the behavior of a black box. Now, if you're all familiar with distillation, here what we're doing is basically we're distilling the behavior of a black box to a set of symbolic models. However, these rules are often, they're quite simple and they work well only for a specific subset of data, and they are not often generalizable to the whole data set. So we actually borrow the ideas from the so-called deferral models, which are actually shown in this as these selectors here. So the idea of a deferral model is like this. Say you have an AI model, which will be deployed along with a clinician. Now, the deferral model is actually a classifier that can be viewed as a selector that chooses between the AI and the radiologist or the clinician. When it is very confident, it uses the AI model's decision. When it is not, it defers the decision to the radiologist. So basically, the idea is that the difficult samples will go to the radiologist. For us, the selector is also a classifier, and this is like a one-layer neural network, which is a very shallow classifier that chooses between the symbolic model or the black box. When it is confident, it actually uses the symbolic model, and when it is not, it defers its decision to the black box. For each iteration, it actually has a budget, say for example, say 20%. So basically the selector for every iteration covers at least 20% of the data and distills the knowledge from the black box to the corresponding interpretable model. Specifically for this iteration, say for iteration 1, we learn the first interpretable model, which is G1, and the first selector jointly using a knowledge distillation loss from the black box. And for these Gs, we use the state-of-the-art ELN or entropy-based logical neural network, because we not only want to predict the label, we also want to predict the first order logic. And this ELN, they have a mechanism which will gonna give us the first order logic in the form of concepts. We just use them. We didn't change anything, in the architecture of ELN. So is this part clear? So for example, I can give you if I do a TLDR after this iteration, this G1, which is the interpretable model, it will be carved out from the black box, and basically it will become specialized on, say, these samples, which may be like the 20% of the entire data set. So that's like for first iteration. Now, whatever things that are remained, we refer to them as residual. So here we basically copy the initial feature extractor of the network phi and to the next step, and we basically optimize the last layer of the neural network to specialize for the residual data. So if the first interpretable model here, it actually covers, say, 20% of the data, then this residual will specialize on the remaining 80%. Thus, the residual will become the black box of the subsequent iterations, and we continue the process. So what here we are learning, so those who are familiar with LIME, so it actually learns local approximation functions, which actually mimics the behavior of a black box in a small region. So we are also trying to do the same. Likewise, we continue to the next iteration. We train another selector, another symbolic model to cover new portion of the data, say another 20%. And there will be some residual left, and we continue the process. And effectively, at the end, we're going to end up with these three symbolic models that are extracted during the different iterations of the method. We call them as expert as they specialize on various subsets of data. As a result, we end up with a mixture of experts, each of which are simpler functions covering specific subsets of data. Finally, there could be a small residual left, which cannot be covered by any of the expert, and that will be covered by the final residual. And it will only cover the unexplainable half of the data. So is this method clear? Or do you have any questions? I can take any questions. Okay.
So here, sorry, Shantanu. So
Yeah.
here you are actually defining your residual based on the concepts, right?
Yes.
Mm.
Yes. So the residuals actually the black box for the next iteration.
Right, but the G function that you are referring to, they are actually defined based on the concepts.
Yeah, they are basically based on the concepts. Yes. So the
Right,
concepts will be the input to these G functions. Yeah. Yes.
right. And your phi actually, which is a feature extractor, it stays the same throughout all your iteration.
Yes. 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 Otherwise, it will become very expensive.
Right, right.
Yeah.
Those ground truths for the G function is going to be same for all these three steps.
Yeah. So the ground truth of the G functions are actually the class labels. So the G functions will gonna take the concept probabilities as input, and it will gonna try to predict the final class label. So the way it is actually trained, it is not actually the final. We did not train it as a final class label. We actually train it with the supervised logics coming from the black box using the distillation loss. This is basically distillation.
Right.
Shantanu, one question from my side.
Yes.
The symbolic models at each stage, they're going to be different based on like whatever residual is left, right? So
Yes.
basically different rules are classifying at the
Yeah.
first stage, and then whatever
Yeah.
remains, there is a different
Yeah.
set of rules for that, and then
Yeah.
on
Yeah.
and
Yeah.
so
Yeah. So we are basically trying to learn local approximations of the complicated
okay.
function that is learned by the black box.
So
Okay.
are you selecting the part of the data to be used by different selector, or
No.
this is
That is
automatic, right?
it's automatic. We only set the threshold, which is like say
Okay.
20% or 15%. That's it. But that 20% will be learned automatically.
Okay.
Okay. Cool. So we actually compare our method against two baselines. So now there is like a plethora of concept bottleneck models. So at that time, it was mostly two. It was the initial concept bottleneck model, which is the interpretable by design, and the post-hoc concept bottleneck model, which is developed by Professor James Zhu's group in Stanford. So we compared against these two. Now in these two models, they have the logistic classifier, which is actually attached after the feature extractor. Now, if you remember that we are aiming to get the first order logics, and we are using ELAN architecture as the G's. So to have this apple to apple comparison, we replace the logistic classifier with the ELAN so that the baselines will also gonna produce the class label and the first order logic. Okay, so let me first give you the qualitative example on the toyish dataset, which is the CUP200 dataset, which is a bird dataset. Now, the concepts here are the color of chest or wing or shape of the beak. Now, here is an example of the rules learned by the first expert. So you can see that the first expert uses the concepts like breast color gray and tail pattern solid to identify these set of birds as olive-sided flycatcher. For expert number 2, it actually uses some other concepts, which is like underparts color gray and wing color gray to identify this bird as olive-sided flycatcher. Now, I did not show the first order logics from the baseline, but if you use any sort of baselines, you can see that the baselines, they actually will gonna have one first order logic with all these concepts jumbled up to explain all the different birds. And that is where our method is different from the baselines. Like we are learning these local concepts for a subset of data. And finally, you may end up with this particular sample, which is not at all covered by any of the experts, and it will be covered by the final residual, and it will gonna remain unexplained. In our paper, we empirically observed that the earlier experts, they actually focus on the easy samples, and the samples will become gradually difficult and difficult as we progress towards the deeper iterations. And we use a popular the sample level difficulty metric to justify our claim. So next we show that our method does not compromise the performance. So here we are aiming to carve out the mixture of experts from vision transformer based black box for CUP200 dataset. And the performance of the black box is actually this dotted line, which is actually the upper bound of different interpretable models. Here, the black box achieves 92% accuracy. We can see that, first of all the experts in our method, they cover 95% of the samples. And for those 95% of the samples, our method consistently outperforms the baselines. And this is also true for other architectures as well for the same data set. And you can see that the gap between the performance of the black box and our method is minimum compared to the baselines. This is due to the fact that the experts in our methods, they specialize on specific subsets of data compared to the baselines. The baselines use one interpretable model and it hope to perform well, or it hope to learn a function which is gonna fit to all the samples. Now in this experiment, we actually show that the residuals perform poorly across different iterations. And this is actually one of the first insight that actually was used to show that the later experts, they cover the harder samples. So here also, like, we are using CUP200 data set, and we are using VIT as a black box. And these different colors, they represent the different experts. So here we have like 6 experts, and this black one is the last residual, which is left. So in the first iteration, the residual contributes more to the cumulative performance than the first expert. So here, if you do a weighted performance, you can see that the expert one's contribution to the overall performance is minimum. And again, this dotted line is the performance of the black box. Now you can see that when the second expert come in, gradually, cumulatively, their contribution, expert number 1 and expert number 2, their contribution to the performance is gradually going high, and the contribution of the residual is coming down. And if you look at our method diagram, this is where we showed that like the black box will actually gonna go thinner and thinner, and it will become weaker and weaker as we progress towards the deeper iterations. And it actually continues likewise. And finally, it ended up having the minimum contribution to the final performance. Now, if you remember one of the motivation slides, I talked about something called recourse or intervention. So now those who are familiar with concept bottleneck models, the biggest advantage of using these models is that if you don't like the decision of these models, you can of course have an oracle or a domain expert, and they can change the concept values or those probabilities, and they can alter the decision of the model. Now, one thing is, what we can do is that, of course, we can intervene on all the samples, like all the misclassified samples. But what is interesting in our case is that our method, it actually finds out the difficult samples. So just I mentioned that the later experts, they actually cover the difficult samples. So one advantage is we can perform the test time intervention only on these hard samples. And by hard samples, I mean that the samples which are covered by the final 2 experts. So here, for example, the expert number 6 misclassifies this fish crow to be a brewer blackbird. We can replace the concept values with oracle, which is like the ground truth concepts, based on the magnitude of the attention weights of the model. And when we send this updated concept vector back to the model, it actually classified the bird correctly. So this is the setup of the test time intervention on the hard samples. When we intervene on the top 75 concepts on only the hard samples, we actually saw this performance gain. For example, say for CUP200, ResNet 101, the performance gain was like 5.5%. For VIT, it is like 6.5%. And this is actually consistent for different architectures for different data sets. Okay, so now let's discuss the same for chest X-ray. So here are some qualitative results for MEMX CXR. We aim to classify plural effusion. And you can see that again, for expert number 1, it classifies the second sample, the second test sample, to be of plural effusion because of these 3 identifying concepts, which are like left pleura, right pleura, and unspecified pleura. Whereas expert 2, it did not consider the left pleura. It only considers the right pleura and the unspecified pleura. And likewise, expert 3 uses another set of rules. Expert 4 uses another set of rules. And also for CXRs, we don't compromise the accuracy. Now, this is the plot for plural effusion. Now, one interesting thing is, of course, our method, it outperforms the baselines, but you may see that it actually overshoots the performance of the black box. Now don't confuse, because these blue bar is only for the 90% of the samples that are covered by all the experts, and the performance of the black box is actually for all the 100% of the test data. So there are still 10% of the test data left. So this bar is only for the samples that are covered by all the experts. And one thing is that we continued this process of extracting experts till at least 90% of the data is actually covered. And this is consistent for other diseases as well, like for pneumothorax as well. Okay, so now that we created another concept bottleneck model, with the help of this mixture of experts, now the question is, what is its application? Where can we apply it? What particular problem that we can solve? Now, in our subsequent paper, we actually applied them for data efficient transfer learning. Now, consider that we train a model on one side and we want to deploy it to another side. For example, say we train our model on Mimic CXR data from Boston and we want to deploy it on, say, Stanford CXR. The standard technique is, of course, transfer learning. Now we can fine-tune the parameter of the initial model to predict the labels on the target site. However, it can be inefficient both in terms of data and computation. Why it is inefficient for computation? Because we have to fine-tune all the layers, like the feature extractors and the linear head. Why it is inefficient in terms of data? Because we have to use all the data from the target side in order to do this fine-tuning. However, the clinical rules, they are invariant. So if the method that I just discussed earlier, if it can truly learn the clinical rules, those rules, they don't change from hospital to hospital. Can we apply those clinical rules extracted by the method to solve this problem of inefficient transfer learning? How do we do that? So here is the approach. First of all, we have a couple of assumptions. The first assumption is that in the source domain, which is Mimic CXR in our case, we have the report to parse. However, for the target domain, which is Stanford CXR in our case, we don't have any radiology report to parse. So then the question is, how do we learn the concepts on the target side? So here is what we do. First, we assume that we have disease labels for a very small proportion of patients in the target domain, say 15%. Then we apply the source black box on the label data to predict the disease in the target domain. And then we find some patients on which the model predicts the disease correctly. And for some of the patients, the model prediction is incorrect. These correct ones are actually shown here, as green, and the misclassified ones are shown in red. Now remember that we also have a projector from the source side, which actually predicts the probability of the presence of concepts. We take that source projector and predict the concepts for the correctly diagnosed patient. We assume that these concepts are the true concepts. For the misclassified patients, we don't know any concepts. We don't have any concepts. This is actually the typical semi-supervised learning setup. So we use the pseudo-labeling algorithm in semi-supervised learning to propagate the concept labels by fine-tuning the concept extractor. And thus we learn the concepts in the target domain. Once we extract the concepts in the target domain, learning the mixture of experts for the new domain is easy. We only fine-tune the source experts and the selectors for only 5 epochs on the limited training data on the target domain. Now, fine-tuning these selectors is essential to learn to route the samples in the target domain to the specific experts. Now, here is some result. So the x-axis is the proportion of label data on the target domain available. We experimented from 2.5% to all the way to 15%. And the y-axis is the AUROC. Now, this gray line is the vanilla transfer learning that has been done using the black box on the limited training data. And the blue one is the optimal method where we fine-tune the mixture of experts and the selectors for 5 epochs, and rest are the different ablations. Now you can see that with such smaller amount of data, we actually achieve way better performance compared to the black box. This is because our method focus on the local concepts, which are invariant across hospital to hospital compared to the data-hungry nature of the black box. Similarly, here is the computation performance. And here we are also aiming to classify effusion. So the computation performance is actually in terms of the logarithmic scale of flop count. So the y-axis is the flop count, and where the lower is, the better. The blue one is our method, the red and the blue one. And the gray one is the vanilla black box, and the rest are again the different ablations. And you can see that there is a huge difference in terms of computation compared to the black box and our model. This is because we only fine-tune the experts, which are shallow neural networks, and the selectors, which are like one-layer neural network. And for the black box, we are required to fine-tune its feature extractor, which is generally consists of all the encoders of vision transformers or the convolution layers of CNN and its linear head. As a result, the flop count of the black box is very high. And this is actually consistent for all the different diseases. So what I showed you is effusion. This is consistent across cardiomegaly. This is consistent across edema. Okay, so in summary, post-hoc approach allows the use of the flexible black box models, but they're often inconsistent, and they, most importantly, don't allow the algorithmic recourse where we can fix the behavior of a black box. Now, interpretable by design models, they allow the recourse, but they suffer in performance. Now, in this talk, I show a method where we can extract a mixture of interpretable models from a trained black box, which can offer the best of the both worlds. Each interpretable model, or the experts, they are modeled as first-order logic, and they will become specialized on a specific subset of data. But there are other choices that can also be possible. For example, you can use proto-PNet, you can use decision trees as those Gs or the experts. Now you can use this mixture of experts to solve the problem of inefficient transfer learning. So transfer learning becomes more efficient in terms of data and compute with this new method. And more importantly, intervention on hard samples can be possible with this new interpretable models, or the mixture of interpretable models. And these are all the representative papers. So in future work, we aim to leverage language to detect and fix the black box. We are also specifically interested in its application in breast imaging. I mean, our lab has done many work in chest x-rays, so somehow my advisor got interested in breast imaging now. And in this space, we actually developed the first vision language foundation model for mammograms, which we call MemmoClip. it has just accepted as in MICAI, and we're gonna present our work in MICAI 2024. So feel free to come to our poster. This is the poster number and the date. And if you want, you can also check our project website on MemoClip. And these are like the two QR codes for the work that I presented here. And finally, I'd like to thank my lab mate and my first mentor, Kay, who actually created this entire rad graph pipeline for chest X-rays in our lab. And he also, published two, great publications in MICAI and in RadAI to localize the disease without the bounding boxes. And finally, my heartfelt gratitude goes towards my amazing advisor Kehan for supporting me, guiding me, helping me to write the papers, and he's great. So yeah, and also special thank to Faru, who was also a part of this the first paper. She's from Meta, and she was actually the one who sat with me before my ICML deadline for the whole night to write the feedbacks or to address the feedbacks given by Kehan. So it's so thank you Faru for all your help. Thank you. Do you have any questions? Yeah, I can take it.
Awesome. Thanks so much, Shantanu. I think this was a great talk. Maybe
Thank you.
before we move on to the questions, let's give our speaker a virtual round of applause for the wonderful talk.
Okay. Thank you.
Yeah. Yeah, the floor is now open for questions.
So, Shantanu, I have one quick question. So, I still don't understand the reasoning behind the transfer learning part, because I agree that in medical problem, or even in a generic capturing problem, probably you don't have a change of the concepts, but you have a huge change in the domain, right? Like imagine that there is a difference in the acquisition device, there's a difference in the protocol, so you would have a very big change in your file. I'm not sure
Yes.
if I understand how you're encountering that.
So the way we are so what you are saying is that there can be a lot of the noise, or I would say spurious correlation in terms.
I would not say noise. I would just say that there can be a kind of big shift in the
Big
feature
shift, yes.
extracted part, right? Like which is not only
Yes.
you're covered by your concept, but there is also a big change in the feature space, like image space,
Yeah. So what we assume is that, for example, say if you have one disease, say cardiomegaly or say pneumothorax, and you have some certain rules, some concepts which can be very very applicable towards that particular disease. For example, say cardiomegaly is enlarged heart size. Now, if these rules will become intact from your one domain to another without very major shift, our method works well. For example, there is another data set which is called NIH, NIH chest X-ray, and NIH is heavily plagued with this pneumothorax versus chest tube. So when we try to use our transfer learning method for NIH, it didn't work well as expected, because the data set that the shift was very huge. So here is another assumption that we have is if the shift is not that huge, of course it can work. But if there is some other, even one of my lab mates, he actually found out that in NIH, not only the chest tube, but also the image cropping size also plays a very key role for your downstream model prediction. So that is also another very important, I would say, feature that you need to predict your model, predict the disease very well.
I would imagine, since you are actually taking the Stanford data as your test, probably then your model works, because Mimic and Stanford data has their basic difference, because Mimic is actually captured with the portable chest X-ray mostly, and Stanford is actually the static chest X-ray. So I would imagine that if you train on Stanford and tried it on Mimic, probably you would also see a big shift,
Yes, you are right, and I would love to do that probably now, because the problem back then was that Stanford does not have that concepts. That
Right.
it does not have that reports. Now I think they also publish the reports,
Right.
so it will be quite interesting to see the other way around, and
Right.
probably it will gonna highlight the what you are basically seeing. So we have this assumption that you will not gonna have this major shift from between one domain to another domain.
Right.
That's when this method can work. But yeah,
Okay.
thank you.
I had one question.
Yes.
So at the beginning when you were presenting on the CUB data set, where you were showing the amount of performance attributed by each of the experts,
Yeah.
so around here, the increase in proportional accuracy seems to be kind of consistent. Would that be due to the fact that you're using, what was it, 20% of the data for each of the iterations, or is there somehow that you constrained it such that you get such a proportional increase every time?
So the idea is that as you progress from one iteration to another, you will gonna cover more and more data, right? And
Mm-hmm.
you will gonna learn those local approximators well.
Uh-huh.
So cumulatively, if you see, the performance will gonna go up.
Mm-hmm.
But there is, I think, in our paper we also showed that the performance of each experts individually, not like so this is like the weighted, not the not non-weighted version.
I
There you
see.
actually show, there will actually see that the performance of the experts are actually going down because the samples are getting difficult and difficult, and it will be it will be also difficult for the experts to behave well on those difficult samples.
Mm-hmm.
Yeah, for the sake of the time, I actually didn't include that result. So that result actually was interesting, where we actually showed that so you can also use this method to find out the difficult samples.
Yeah, that's okay. Really interesting. Thank you.
Yeah, no problem.
I had a question as well,
Yes.
but more on a higher
Yes.
level. In this, in your example with the radiology reports, you have a ready source of concepts that you can use for labeling. But in
Yeah.
domains where you do not have those concepts, or those concepts are not predefined, for example, like in time series data, like with EEG or something, what would you, how would you actually, first of all, develop those concepts, and how would you label each of these instances with these concepts? I mean, it's a hard problem, so I'm just curious if you have any thoughts about.
I actually I don't have actually any answer to this, because one of the things, like one of the two modalities where I work, one is chest X-rays, and now I'm working in breast. So there are like predefined set of concepts. For chest, there are a lot. For breast, there are only 8. But for there are, and we also received this feedback in last year's Mikai as well from Pallavi, that for brain CDs you can also have this problem, like you don't have any concepts, predefined concepts. How will you work? I don't have any answer, quite honestly. Sorry.
No, makes sense. Yeah, I guess it's still an
Yeah.
open problem for research.
Yeah, it's still an open question. Maybe LLMs. So yeah, everybody is using now LLMs, to create a concept bank. Maybe that can also be helpful. Yeah.
Sounds good.
One question about the breast cancer, classification domain. So I work with University of Wisconsin, and we basically, so NVIDIA has this model zoo, which is basically a medical imaging model zoo. Okay, so
Yeah.
somebody published a breast tissue density classification model there. Okay,
Yeah.
it just does the 4 categories like A, B, C, D based
Yeah,
on that
ABCD,
yeah,
yes.
yeah,
Yeah.
and
Based on the
then
density, like, yeah.
yeah. So that was trained, and there is an archive paper. It does very well on the test set on the 4 categories, right? But now when we tested on this University of Wisconsin data set, we have the Docker image. It's open source. I can put a link to that. On 10,000 images, that model is only predicting B and C. So it's basically useless because we know that there is A and D in that 10,000 images, but it's making such a weird error. Like and some cases we visually check. Some cases it's very easy. It's clearly an A or it's clearly a D.
Okay.
But the model is just going towards B and C. And we see this more and more as we start running inference at scale, like I'm talking like 10,000, 100,000 images. Any thoughts on how to go about like debugging or like trying to find what happened?
So one thing for breast, what I found is that for this density is that so there is one density which is, I think this is A, where it is very dense breast.
That is D.
The
D.
D is
That
very
is D,
dense.
right?
Yeah.
Yeah, D is very dense.
A
Yes.
is fatty, only
A is
fatty.
A is fatty. Yes, A is fatty and D is very dense. So I think finding out the density D is actually very hard. And this is also conveyed by the radiologist with whom we are collaborating. When I created the memo clip and when I did this zero-shot classification on the 4 densities, I also observed that for density D, I'm not sure about density A, but for density D, the model actually struggles. The model actually struggled a lot.
Because I think,
So
Shantanu, the main problem is that in the training data set, so you understand, like if you just create a random sample of the training, you would very infrequently have the extremely dense breast.
exactly.
Because which is
Yeah.
super rare, right? So of course the model will have trouble in learning a super rare class.
Yes. So yes. So I also tried with a lot of different stuff, but this is a very open problem. I must say that because the number of samples are like way less.
Yeah.
What we are also doing is that you can get that data set. That's an open cattle RSNA data set. Even in that data set as well, we found actually the same issue, that the number of samples with very dense breast was highly rare, and the model struggles a lot.
Another thing, Mehul, I would suggest you that I don't know if you know that, like we have an NIH project with UW Madison. So we are working simultaneously with UW Madison, all the mammogram data.
Okay.
So the UW Madison is kind of like really strange because they have some outpatient center and their quality of the image is pretty bad. So I would suggest you actually take a look at the intensity histogram. And if you see that, if you can observe a big shift in the intensities, because that's what we observed when we started working with UW Madison.
This is also another important thing. Yes. So the thing is, so there are like this, when you have these dicoms, so there are like normal dicoms, and then there can be something called JPEG compressed dicoms, which are
Right.
completely white images. If you have this kind of shift within your data set, this can create a lot of problem, because those white dicoms, they actually have nothing. And when you actually have this like conversion from those dicoms to PNGs, you're gonna lose so much of information that your model will not gonna learn anything meaningful. So this is another interesting pointer that Iman mentioned here. You also saw the same thing.
Okay, thank you.
I think so.
Iman,
Cool. I guess we are almost at time. Are there any other last questions?
I'm sorry. Thank you for the link. I'm gonna take a look in these models. Thank you for that. Yeah.
Great. If there are no more questions, then perhaps we can end the session today. Thanks again, Shantanu. We'll have the YouTube video up later this week, and if anybody has further questions, feel free to get in touch with Shantanu or reach out to us, and we'll be happy to put you in touch with him.
Yeah, sure. Thank you.
Thank
Yeah,
you.
thank you.
Bye.
Yeah, thank you. Have a good one. Bye.
Thank you. Bye-bye.